Yes. So you're able to see my screen, right?
Yeah, ma'am.
Okay.
Yes, ma'am.
Okay. Now let's start the session. So I welcome you all for the second live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. And I am Kritika and I am handling this live session. Okay. Uh, let's get on to the session. So as usual, we'll have a brief recap of the week 2 lecture and then followed by some practice assignment questions. Okay. So this is going to be an interactive session. Okay. And I request you all to actively participate. There is nothing right and wrong. Whatever you remember, you can say. If it is right, it's good. If it is not right, don't worry about it. You're going to learn. That's it. Okay. And I request you all to just go through the lecture before the session so that if you have any doubts on the lecture, you can get it clarified during the live session. Also, you can post your questions in the forum, and that will be answered. Okay. Hope you all got my point. You're able to hear me clearly, right?
Okay. Yes,
Okay.
ma'am.
Okay. Okay. Then let's get into the session. So the week 2 lectures had lectures. There were 8 lectures. So it started from lecture 8 and ended in lecture 15. So lecture 8 was on renewable sources for polymers. So it was on the sustainability. So there was a discussion on sources of polymers, right? So what were the sources that was discussed? Someone remembers from where you can get polymers, the sources. So one was on renewable sources, the other is obviously the natural sources, right. So it differed based on the feedstock also. So what is the feedstock that is used for synthesizing the polymer, whether it is from non-renewable petroleum based sources or is it from the natural sources, right. So and there were discussion on whether it if it is natural source also, whether it is really biodegradable, and the biodegradability and the cycle, the cycle time it takes for biodegradation, it really determines whether it is actually biodegradable or not, right. And there were discussion on natural fiber composites, correct. So they were discussion on what are the natural fibers used and all, right. So the natural fibers, they can be from plant sources like sisal, coir, jute, right, bamboo, pineapple. These from these you can get the natural fibers. And then there was a discussion on sources from animal also like silk and wool, right. And there were some practical examples, right, where these natural fiber thermoplastic composites were made with jute in combination with LDP, HDP and all, right. Are you all there?
Yeah, yes, ma'am. Yes, yes.
Yes, ma'am.
Okay, okay. Because once I go into the presentation mode, I may not be able to see you all. So I just want some response, at least yes or no. Okay. I should know whether I'm still connected or I lost my connection. Okay. Right.
I have a
And
question. This renewable actually mean by what is the actual term renewable?
see, it here it actually means the source, because when you just get into the renewable source, like right from plants, for example, take pectin or you take cellulose, so you can easily get, it gets continuously replenished. Some new plant will be growing and it happens, right. It's there all around. Whereas when you consider non-renewable source, your petroleum based, it takes a lot of time uh, uh, you know to get these petroleum products, right. And these polymers from the non-renewable petroleum sources, so that will again depend on these non-renewable sources because they are byproducts of some petroleum processing, okay. That is what is actually about this renewable and non-renewable source. See, end of the day, these plants degrade, and due to this further processing and all, only you will get into these petroleum and crude oil. But
No,
what is
my
the
doubt is that renewable means it is plant based or
it's
something
not
else.
it's not only plant based, even animals, bacteria. So you can synthesize polymers from bacteria. For example, you can synthesize cellulose fibers from bacteria. Okay, like in vitro, that is in a lab you can synthesize. There are certain bacteria that can synthesize nanocellulose.
Yeah, that I heard means I read recently
Yes.
xanthan gums.
Yes, xanthan gum. Yes, xanthan gum is another example from microorganism. Okay,
Yeah.
and similarly, this polyhydroxybutyrate, that is also from through microbial reaction only.
So that means the renewable means it is already the polymer is made by some natural sources. It's
Yes,
already by yeah,
it's not only already made by. Sometimes you just see, for example, you would have heard of this fermentation process and all. Okay, so in fermentation
yeah.
process, you just give some bacteria or fungi or something, the required food and everything, and physical conditions like temperature, whether some may require some acidic condition, some may require some neutral condition. So you, and then it may require some food for it to grow, and then they may exude some polymers through in their extracellular matrix and all. So that is also so that is you can synthesize in lab. See, for
So what
example,
about the natural rubber?
natural rubber is again a renewable, but only it's from plant, right? But only thing is
Yeah.
that the degradation, of natural rubber is a question, because it takes much longer time. That's it. But it is again a renewable
Yeah.
source only. But the second,
So
yeah, tell me.
renewable sources means it should have the origin and degradation in both ways. It should be naturally blended, no?
More, yeah. See, degradation, end of the day, everything should go into the biogeochemical cycle. But
Yeah.
as a source, as a feedstock, if it is going to use some natural sources like from plants or animals or microorganisms, then it is of a renewable source. I think, hope you got it.
Yeah, I got it. Got it.
Yeah, fine. Okay. Uh, okay. Can we just proceed? And then, strategies for using the renewable source for generating polymers were also discussed. Like, for example, in place of polyethylene, why can't we mix a polyethylene with starch, a partial replacement, or a composite with a natural fiber, right? And then modification of the natural polymers, because natural polymers you may get some cellulose, some pectin, but it may not be actually usable for the commercial application what we are looking for. So we need to modify it in some way so that it is actually useful for the commercial application. So modification of that. So these are some of the strategies that was discussed. And then the polymer from renewable monomer like polylactic acid, and then from microorganism polyhydroxybutyrate. So these were all discussed in the lecture 8. And then you the next lecture was on polymerization and depolymerization. This was again on sustainability, right? This was again on sustainability. So the polymerization method for each polymer, and then ionic polymerization, where anionic and cationic polymerization was discussed. So someone remembers which was a living polymerization that was discussed in polymerization technique?
And
Yes. Okay.
well,
Anionic polymerization. Yes. Okay. That's good. And what are the new ways to think about the polymerization, and what are the control parameters for a molecular structure in case of biopolymers, right? How do which are the points of concern for controlling the microstructure for biopolymers, like for example for proteins, for polynucleic acids, and then for polysaccharides. So for example, for polysaccharides, it's not just one parameter. It requires a sequence which is is the point of control, and then the regio and stereo isomerism, types of linkages, branching density, and the length of branches, networking, cross linking, all these come into how do you control the molar mass, correct? So these were all, because natural polymers again, they start from oligomers to extremely high molar mass materials, correct? Correct. So someone remembers,
Correct.
which is having a narrow, molecular weight distribution, and which has a broad molecular weight distribution among natural polymers. Uh, which has a very narrow or very specific molecular weight distribution, and which has from narrow to broad range distribution among natural polymers. Natural polymers, I'm just saying on polynucleotides, and then polypeptides or proteins, and then polysaccharides. Among these, someone remembers? It is actually for polynucleotides and proteins. You have a very narrow distribution of your molar mass. Whereas in case of polysaccharides, it may range from narrow to very wide distribution. That's what yesterday during the class I was showing for pectin. I just showed a polymeric chain of galactonic acid, and then I said that it has much more, like it may have some Ramnos units in the main backbone chain itself, and then a lot of side groups as well, a lot of side group sugars as well. So it is much more complicated, I was saying. Hope someone remembers that. Someone
Yeah,
remembers? Okay, okay. And then the in vitro and in vivo polymerization. So in vivo, it happens through bacterial polymerization that was discussed, and then in vitro using an enzyme as a catalyst. And then what are the depolymerization techniques, especially in case of biopolymers? There are a lot of enzymes that are involved, like depolymerases, hydrolases, right? So these were all discussed in lecture 9, correct? And then
yeah, ma'am.
and then lecture 10 was on states of polymers, right? So you have a liquid like state, solid liquid like state, solid like state. So someone remembers what are the liquid like state that was discussed? Some liquid like state. It is actually there in the slide as well. It is polymer solution and polymer melt, right? And your polymer melt is basically for the fabrication and processing. That's where this liquid like state is playing a role for polymer melt. Whereas polymer solution, it also plays a role in, it is also there in applications, right? And then what else was discussed? So what are the interactions, weaker and stronger interactions? What make, in which case it is a weaker interaction? For example, in liquid like state, the interaction is weaker, whereas in solid like state, the interaction is stronger, right? So if it is a weaker interaction, then it is more liquid like and less solid like, right? If it is higher temperature, again it's more liquid like and then less solid like. If there is a solvation or plasticization, then there is a weaker interaction, right? That means again more liquid like, right? Right? And then there was discussion on solid like states, solid liquid like states, polymer gels, and then liquid crystalline polymer. So do you remember, someone remembers what was the difference that was told, especially on polymer gel and a polymer solution? Both has polymer and then a solvent. But what was the difference?
Polymer solution is the polymer is going inside the solution, but the polymer gel, the solution is going inside the polymer matrix. What I think.
Okay. Okay. The key difference is that the cross linking. Okay. In case of polymer gel, you have a cross linking, and the interaction of the cross linking, it plays a critical role. And in fact, as you said, in polymer gels, so between the cross links, you have the solvent molecules. Okay. And then there was a discussion on liquid crystalline polymers, and then solid like states like rubbery, glassy, and semi crystalline states were all discussed, right? Right. So let's proceed to the next. Lecture 11 was on application based terms. So this was on uses. So types of polymers based on application was discussed, right? So there was a discussion on plastics and rubbers, thermoplastics, thermosets plastics. So what is the difference between thermoplastic and thermoset plastic? Someone remembers the basic
That
difference?
is very simple.
Huh?
Yeah, it's very simple. Thermoplastic you can reuse several times, but thermoset once you cannot melt again.
Yes, perfect. So thermoplastics, it can be melted upon heating and you can recycle it. Whereas thermosets, it is completely cross-linked. It's a 3D network, right? In fact, it forms a 3D network. The liquid actually form of the thermoset is the resin, and the molecular weight actually builds up upon polymeric reaction and cross-linking, right? So you need to add a curing agent or a hardener. So the best example is a epoxy, uh, thermosets, right? Epoxy with the hardener, epoxy hexamethylene diamine, right?
Yeah.
Where, yeah,
Yes.
so that was an example. And then polymers,
Phenol formaldehyde, epoxy, lot of resins are there, and even natural rubber after sulfur cross linking it become thermoset.
but still you have that in one difference is that this becomes this natural rubber, the interaction is weaker and the cross links are lesser compared to your epoxy.
Okay, I agreed. Yes.
Yes, yes,
Otherwise, it
and
is called a ebonite.
still you have the
Ebo-
flexibility.
but if you think about ebonite, it is reverse.
Okay. Okay.
Okay.
And then polymers are also used in electronics, fuel cells, batteries. So you have conducting polymers, right? Someone remembers any conducting polymer?
Conjugated dynes.
Acetylene.
Yes, polyacetylene. Yes, yes, polythiophene. So they have the
Yes.
uh, conjugated bonds, right? And then ionic polymers are there, and which is one of the very popular ionic polymer, which is like used in fuel cells.
Acrylate.
Nafion.
Nafion, yes, yes. So what is that ionic group present in that? Someone remembers? It is actually the sulfonic acid group,
Fluoro.
SO3H group. So it is actually Teflon backbone where this SO3H group is actually incorporated. Okay, and then you have polyelectrolytes, polymer charge complexes, dielectric elastomers, right? These things were discussed, right, in the part of application. And polymer composites where you have the polymer resin matrix, and there can be a filler or reinforcement, right? Filler you generally say when you just want to cut the cost, reduce the cost. Whereas reinforcement means there is some property enhancement, but this is also kind of interchangeably used. Sometimes, when you go through these research papers and all, they'll say that, the carbon fiber or graphene fillers were used. There, it doesn't mean that, it is just cutting the cost. In fact, graphene are all costlier, producing this graphene nanoplatelets and also that there it actually helps in improving the conductivity of the system. To improve the conductivity of the polymer matrix, they add these graphene fillers and all. Okay, so these were all discussed, right?
Yes.
And then lecture 12. So lecture 12 was again on sustainability. So how do you reuse and repurpose? So the concept of linear and circular economy was discussed. Ecological and carbon footprint, how do you reuse? And it doesn't mean that if you're reusing, you're reducing the ecological and carbon footprint, or you have to see a lot of aspects also. You cannot just keep on reusing also. Sometimes that may also cause some diffusion of some small molecules which may actually have a health concern as well. So those things are also to be really looked into when you're reusing and repurposing it, right? And we have to check on the carbon footprint. Right, do if it is really giving a lower carbon footprint because of on reusing and recycling the materials. So this was discussed in lecture 12, right? Are you all there?
Yeah, ma'am.
Okay. Then lecture 13 was on molecular conformations, right? It was on concepts. So what is a conformation? It started with what is a conformation on ethane and butane, the simplest uh, molecules, from where the essence of the conformation in polymers was brought in, right? Because these simple molecules itself will have different conformation because of the CC bond rotation, correct? And there will be some conformation where you will have minimum energy, and there will be some conformation where there will be maximum energy, and the minimum energy conformation is always favored, correct? Right. So what are the roles of conformation in each case? See, for example, in a crystalline material, it will be more of a bond vibration, right? Whereas when you go for glassy systems, under glassy conditions, you will have bond vibration as well as side group rotation. And when you go for a rubbery or a gel like system, there will be segments. The polymer segments will have mobility, correct? So these were all discussed. And then what are the statistical property of single macromolecule? So how can you really, understand the overall bulk behavior from a single after understanding a single macromolecular behavior, and how it really has an impact on the overall polymer behavior, was discussed. So length and direction vector connecting the first and last carbon atom, right? So this was discussed, right? End-to-end mean square end-to-end distance, and the distribution of end-to-end vector, right? And the orientation correlation, right, between the ith bond. These were discussed. Are you all there? You're able to follow?
Yeah, ma'am.
Yeah, okay. And then in the lecture 14, here again there was continuation on more on the single macromolecules, right? Size, mobility, and flexibility, and this was on properties. So the statistical property of single macromolecule, where different models, the ideal chain and freely rotating chain model, the extended chain model was discussed, right? And the use of and application of single macromolecule model, like size of molecules in solution, overlap concentration, the concept of intrinsic viscosity, how it really affects in different conditions, right? And the flexibility of macromolecular segment, like in rubber elasticity, swelling in polymer gels, and then the concept of radius of gyration, right? And how the shape of the molecule. So the initially whatever we discussed was on size. Now it is on the shape of the molecules. Under shear, there will be a change in shape, and how does it affect the behavior? Similarly, molecules under charge, right? And then the expanded chain model, where you have the excluded volume interaction. So this was similar to your van der Waals model, right, in thermodynamics, right? Right, someone remembers that correlation that was said. You have that V minus B in your van der Waals equation, right? Gas equation, van der Waals gas equation, compared to your ideal gas equation. This also has a similar concept of the excluded volume, right? Are you all there? And then the macromolecule as a Hookean spring was discussed. The potential for a Gaussian spring and the force, right? These were all discussed. And the final lecture was on polyelectrolytes. So, what is an electrolyte? What is polyelectrolyte? And then the examples of polymeric systems with charges which are not as a part of the macromolecules were all discussed. And application of polyelectrolytes was discussed. And then, there was a discussion on sulfonated polymer, naphthalene, in fuel cells. Right? Are you all able to follow? Are you all there?
Yes, ma'am.
Okay, okay. So these were all discussed in the week 2 lecture content. Now let's get on to the practice assignment questions. So now I want every one of you to interact and answer. Okay. The initiator system, which can be used for free radical polymerization at 5 degrees centigrade, is it FeSO4 plus tertiary butyl hydroperoxide, or is it bis iso butyronitrile, or is it potassium persulfate, or is it benzoyl peroxide? So which of the initiator system can be used for a free radical polymerization? This is again a gate question, gate 2022 question. Which of these these forces, materials do you think will help in free radical polymerization? So free radical polymerization means obviously it should form free radical, right? So the
All are
initiator,
free radical, but the temperature is the problem.
is it all?
I think benzoyl peroxide is free radical is producing. I think besides isobutronitrile is also. I think A and C. I don't know.
Okay.
Peroxide is itself. It's means free radical.
Okay. Okay. So
Uh,
does anyone else want to give a try?
Name D. I think benzoyl peroxide because due to peroxide linkage.
Okay. Okay. So I got one saying all are form free radical. The second person said it is benzoyl peroxide. Any other answers? Any other answers or thought process?
Ma'am, potassium
Odd
persulfate.
one is A. For me, it's A. What I believe.
Okay. Okay.
C is the answer, ma'am.
Okay. So some are saying A, some are saying C, some are saying D. So anyone else wants to give a try? Anyone else? Anyone else wants to give a try? Or shall I proceed with the answer? I think I'll go ahead with the answer. The answer is actually A, C, and D. Because as you all said, here it is again hydroperoxide. It's a peroxide. The first one, FeSO4 plus tertiary butyl hydroperoxide. There is a peroxide group. And then similarly, potassium persulfate. And then benzoyl peroxide, again peroxide. So these are all, initiator systems that can be used for free radical polymerization. Okay. So many cases there may be multiple answers. It need not be necessarily single answer. Okay. You all got it? So shall we go for the
Yes.
next question? Okay. So the estimation of the molecular weight of a polymer by gel permeation chromatography is based on is it based on polarity, or is it based on size, or is it based on adsorption to stationary phase, or is it based on crystallinity?
Size, ma'am.
It is one answer, size. Anybody else wants to give a try? Someone else wants to give a try on this? Or shall I just lock size?
Size. Size,
Size.
because it is not crystallinity, it is not polarity. Uh, Size.
Yes, you're all right. It is size. So this was actually discussed when we were when there was a discussion on the molecular conformations. In that lecture, there was a discussion on size and shape, right? Role of size and shape, where your gel permeation chromatography was discussed. So it's size, as you all said. And this is again a GATE 2014 question. Okay, now let's go on to the next question. So this is a numerical problem. A polymer is synthesized from 2 moles of terephthalic acid. The molecular weight of the repeat unit is 132 gram per mole, and then 1 mole of ethylene glycol. The molecular weight of the repeat unit is 60 gram per mole, and 1 mole of butylene glycol. The molecular weight of the repeat unit is 88 gram per mole. The reaction is terminated at 99% conversion of the acid. The number averaged molecular weight Mn bar for the system is dash. So how to proceed with this problem? This is again a GATE 2021 question. So they have given 3 monomers, right? And they have given the number of moles of the monomers also for the reaction, polymeric reaction, and the weight of the molecular weight of the monomer. I mean, as a repeat unit in the polymer. They have not given the complete molecular weight, but the repeat unit, how it will be in the polymer. So that molecular weight is given. They have given that the reaction is terminated at 99% conversion of the acid. They have asked for number average molecular weight. So how to proceed with this? Any thought process? Someone wants to start? Anyone? Or shall I just start solving the problem? Shall I start? Some replies, please.
That is better.
Okay, let me start. Okay, so what is given? As I said, they have given 3 different monomers, right? So one was terephthalic acid, and the number of moles is 2 moles. The repeat unit is OC C6H4CO, right? And then the molecular weight of this repeat unit, this portion alone, without that. So if you look into, you don't have that OH. So the OH is removed. So this repeat unit molecular weight is given as 132 gram per mole. Next, similarly, ethylene glycol, they have given 1 mole. And the repeat unit they have given, and the molecular weight of the repeat unit is also given 60 gram per mole. Similarly, butylene glycol also 1 mole, and the molecular weight of the repeat unit is 88 gram per mole. Right? Now, what should we do? We have to find out the molecular weight of the monomer formed by condensation. Right? MO, the complete monomer formed, because it will have a unit of terephthalic acid, it will have the unit of ethylene glycol, and it will have the unit of butylene glycol also. Right? So, how do you calculate that? So, it is very simple. You have the number of moles and the molecular weight of each component, right? So, number of moles of terephthalic acid and molecular weight of the repeat unit of terephthalic acid plus number of moles of ethylene glycol into molecular weight of the repeat unit of ethylene glycol plus number of units of butylene glycol into molecular weight of the repeat unit of butylene glycol divided by the total number of moles. So that will give you what is the molecular weight of the monomer that is formed. So if you just incorporate the values, so 2 into 132 plus 1 into 60 plus 1 into 88 divided by 2 plus 1, you get 103 gram per mole. The next question, information they have given us, it is 99% conversion of the acid. The reaction gets terminated. That means the conversion P is 0.99, right? So, and then they have asked what is the number average molecular weight. So you have the relation, the number average molecular weight is molecular weight of the monomer divided by 1 minus the conversion. So molecular weight of monomer we know 103, and then conversion we know it is 0.99. So 103 by 1 minus 0.99, you will get the number average molecular weight to be 10,300 gram per mole. Okay, this is how you solve the problem. Okay, now you all got it? Are you
Yes, ma'am.
okay? So can I move to the next question? Okay, I'm just moving to the next
Sure, ma'am.
question. Okay. Now, among the polymerization methods listed below, the one that is likely to give a polydispersity close to unity is
Anionic.
anybody else want to give a try? Is it anionic or is it cationic or is it condensation polymerization or it is radical polymerization? Which one of the following? I got one answer which is saying that it is anionic. So everyone wants to agree to that, or you have any other option in your mind which you want to say? Any other answers? And who told anionic? Why do you think so it is anionic?
Ma'am, it's a living polymerization. All polymers should polymerize, then only it will be ending. There will be no left out anything.
Okay. So I think I am not getting another answers. So as you said, it is right. It is anionic polymerization, and as you said, it is a living polymerization. And until the monomer lasts, you will have the polymerization reaction continuing, and this actually helps in controlling the molar mass. So, and that is why you end up with a dispersity, polydispersity closer to unity. Okay. Okay. Now let's proceed to the next question. Identify if the statement is true or false. Lignin is degraded by few and special microorganism and at low rates. Is it true or is it false? Lignin is degraded by very few and special microorganism, and the rate of this degradation process is also very low. Is it true?
False.
Why do you say it is false?
I think lignin is natural based, so it should be in the very fast way to degrade.
Okay. Okay. So we have one answer and the respective defense. So someone else wants to, say anything else on this, or you all agree with that? Someone, if you are not able to actually, unmute and speak, you can just type in the chat box as well. Okay. I see some message in the chat box. A old message. So do you all agree to, someone answered it. I don't know who answered it because I was on the presentation mode. So do you all agree to that answer or you have a different contradicting answer? I need some reply, please. Or shall I say what is the answer? Okay, I don't get any replies. I'll proceed with the answer. Actually, the statement is true. Lignin is degraded by few and special microorganism and the rate is very low. Uh, And the fact is that though it is from a renewable source, the biodegradability is very low. In fact, this lignin only, over the years it gets fossilized and you will get into biofuels. Sorry, not biofuels, your fossil fuels like your petroleum and all. Okay, so the degradation, though it is from a natural source, the biodegradability rate is very very low. Okay, that is where over the hundreds and several hundreds of years you will since this biodegradability is very very low, you end up in fossil fuels, the petroleum fuels, crude oil. Okay.
Okay,
What?
got it.
Okay. Next question. Control of molecular structure in proteins and polynucleic acids is in terms of. So what is the which one should be considered for controlling the molecular structure?
Side chains.
Is it side chains? For controlling the molecular structure, the molecular weight and things.
I mean side group.
Is it the side group? I'm not saying you're wrong, but I'm just asking if you have any further defense or some point, substantiating that whatever you're saying is correct. I'm neither saying it is right or wrong. Okay. Anyone else wants to give an answer? Come on, you can just give a try. There is nothing right and wrong. Are you all there? Just give a try. Okay, I don't get any replies. It is actually the sequence. You would have all heard of this protein sequencing, right? DNA sequence, right? So sequencing, is one of the critical parameter of controlling the molecular structure in proteins and polynucleic acid. Okay, you would have heard of this protein sequencing. What are the amino acid sequence? Correct. Different amino acid sequence they control, and then your DNA sequencing also, right? So that is what is a controlling plays a role in controlling the molecular structure. Okay, whereas when you consider this polysaccharides, then lot other parameters also comes. It is not only the sequence but your stereo and regio types of linkages, and then your branching density, the length of branches, the cross links, the networking, all these comes. But whereas in terms of proteins, and polynucleic acid, it is the sequence. And that is why you have very very narrow distribution of your molecular weight in case of proteins and polynucleic acids. Okay, you all got it? Hello,
Yeah,
are you
ma'am.
all? Yeah. Okay, let's go on to next question. Molecular interaction in starch is dash compared to polyethylene due to dash. What do you think of molecular interaction of starch and polyethylene? Are they same, or one is stronger, the other is weaker?
Polyethylene is dipole.
Huh? Can you repeat, please?
Polyethylene, the interaction is dipole interaction.
No, I'm actually not asking on what type of interaction, whether it is a strong interaction or a weak interaction, or both. Your starch and polyethylene are having comparable interactions. And if it is strong, then what makes it strong? What kind of interaction actually makes it strong? And if it is weak interaction, what kind of thing it makes it weak? You want to give a try, someone? At least you could say it is strong or weak, right? Either it should be strong or weak or comparable. Something you can say, or that is same.
No, because I'm in a big doubt because if I say polyethylene is very weak, but it is not biodegradable. Starch is, if it is strong, it is biodegradable. So I'm in confused.
Okay. 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 See, biodegradability not only comes in terms of, yes, as you said, the interactions also, but also on the backbone, the side groups. Okay, that also plays a role. Lot of other parameters plays a role. This as such, whether it is strong or weak interactions, as you said, rightly said. When it comes to the after the usage or cycle, then a lot of parameters you have to think of the biodegradability and all. But as such, the straightforward answer is starch has stronger interaction compared to polyethylene because of its hydrogen bonding. When you take natural polymers, one of the very common interaction you will find in all these natural polymers, whether it is cellulose or starch, or is it pectin, you will have strong hydrogen bonding. The strong hydrogen bonding, sometimes if it's a mix of cellulose, starch, pectin, hemicellulose and all, we do not know which is actually giving the highest strength or which is actually playing a particular role in a particular mechanism, because there will be a hydrogen bonding interaction between the within the starch molecule and also between starch and cellulose also. So this hydrogen bonding is one of the very common and kind of a very strong interaction in natural materials. Okay, now let's go to the part B question. Molecular interaction in polystyrene is dash compared to polyethylene due to dash. Here again it is going to be strong or weak, and then due to what?
This is also strong due to bulky side group.
Yes, that's perfect. It's because of the polystyrene has that benzene in the side, in its structure, side group, and because of that bulky side group, it has a stronger, molecular interaction compared to that of polyethylene. Okay, hope others got it. You all got it? Okay, now let's move on to the next question. Thermosets are dash cross-linked compared to elastomers.
Fully cross-linked.
Okay. Any other answers? Or you agree with the answer? It's a very simple question. Yes, it is highly cross-linked. Okay, the thermosets, the degree of cross-linking is very high compared to your elastomers. Okay, and that is why elastomers you still have some flexibility, whereas thermosets it's very less. Right? Next, ecological footprint is estimated in terms of dash, while carbon footprint is estimated in terms of dash. So this was on this, linear and circular economy. In that lecture, it was the ecological footprint was discussed, and then the carbon footprint was discussed. Someone remembers any of these? Any idea, or shall I just go ahead with the answer?
No idea.
Okay, so this ecological footprint is actually estimated in terms of equivalent land units. Okay, and your carbon footprint is in terms of CO2. The total greenhouse gases is estimated in terms of CO2 emissions. Okay, so if you look into the complete understanding of this ecological footprint, this is actually an indicator that can be used to track the past and current human pressure on the biosphere's capacity to provide life supporting and regulatory ecosystems, products and services, and this is calculated in terms of equivalence of land units. Okay, so sometimes even a natural material, in fact in that lecture it was shown that the equivalent land units where a hemp is used, it uses a much more land units. You end up in an ecological higher value of ecological footprint compared to a glass fiber, which has a very lower ecological footprint. So it is not only just about natural materials or something. We have to look into multiple aspects actually when you are thinking of the renewability, sustainability aspects. Okay. Now this next question. Following is a list of some applications of polymeric systems in electrical and electrochemical applications. Okay, so you have some applications like battery electrolyte, proton exchange membrane in fuel cell, separator in battery, gel electrolyte. So these are some of the applications. And the next list describes the polymeric systems that can have ionic conductivity. So what are the polymeric systems given here? Swollen networked polymer, sulfonated polymer, polymer charge complex, porous polymer with electrolyte in pores. Okay. Now what you have to do is match the following polymer with polymeric system and application. So the next list has polymers. You have to match it with the polymeric system discussed earlier, this whether it is swollen network polymer or sulfonated polymer, or is it polymer charge complex, or is it polymer porous polymer with electrolytes in pore, and the application, which application it is used for among the 4 listed application. Okay, hope you understood the question. You all understood the question? You have to match the polymers with 2 different aspects. One is the polymeric system, what type of polymeric system it is, and what application it is used for. Are you all there? What happened today? I think yesterday there was a lot of enthusiasm and a lot of answers. Today you are all very silent. You can just give an attempt. Okay, there's nothing right and wrong. Okay,
Okay, we'll try. Okay.
yeah, just give a try. Okay, Nafion. So what is a polymeric system and what application it is used for? We just
As you
discussed.
said, it is fuel cell. Fuel cell is means battery electrolyte.
Is it battery electrolyte? Aren't there any other option in this set of options?
Yeah, separator in battery also is there. So application, yes, system. And you said this is based on sulfonated.
Okay, so you're saying it is based on sulfonated polymer, and what is the
Yeah.
application?
Fuel cell. Maybe separator because it is a polymer. Yeah, separator.
Is it separator? You have a direct word of its application actually here. We just discussed. One point you got it.
Yes. Fuel cell. Yes. Proton exchange membrane in fuel cell. Yes.
Yes. Yes. So all of you agree with this? You can at least say you all agree or you don't agree. At least you can type in chat box that yes, we agree with the answer. Okay. Anyway, as you said, someone is replying yes. Shamim, yes, sulfonated. Kirtivasan saying sulfonated. Shamim is saying yes, he's agreeing. Okay, good. Yes, Nafion is a sulfonated polymer and its application is a proton exchange membrane. So it helps in transfer of proton, okay, through the membrane, through the Nafion membrane in fuel cells. Okay. And next, concentrated polyethylene glycol with salt. Which one of these? Which one of the polymeric system? And then what application? Just give a try, no? The next question is polypropylene with KOH, what polymeric system it is and what application it is used for. And the last is lithium salt and polyethylene oxide. Which of these? This is actually taken completely from the lecture on polyelectrolytes. This one question is taken completely from the lecture on polyelectrolytes, the final lecture. Someone wants to give a try? Okay, I think no replies. Let's see what are the answers. So Naphion, as you all said, the polymeric system is a sulfonated polymer and application is proton exchange membrane in fuel cells. Concentrated polyethylene glycol with salt, it is actually a swollen networked polymer. Okay, and it is a gel electrolyte. Polyethylene glycol, it actually forms gel systems. Okay, so it's a gel electrolyte. The application is a gel electrolyte. Next is polypropylene with KOH is a porous polymer with electrolyte in the pores. So here the polypropylene role is just the matrix and support. Okay, the KOH actually plays a major role and it is used in a separator in battery. Final is lithium salt and polyethylene oxide. So it is a polymer charge complex, right? You have the lithium salt in the polyethylene oxide. So it's a polymer charge complex and this is used in battery electrolyte. Okay, hope you all got it. You all got it?
Yeah, ma'am.
Yes.
Okay. Any doubts or can we just proceed with the next question? I'm proceeding with the next question.
Just this polypropylene, how it become porous system?
See, you can again design making it a porous system.
Okay, okay, okay. Understood, understood.
Yeah,
Okay,
yeah,
by
yeah.
making.
Yes, 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 yes. It's in the processing. Okay. Yeah. Next question. Role of conformations in terms of macromolecular motion. That is the whole molecule motion. The whole macromolecule moves happens in dash among the following. Which of the following systems you could see the entire macromolecule moving? Whether is it in rubber? I see someone joining. Hi Manshi. Okay, now let's proceed with the question. So, role of conformation in macromolecular motion, where you could see the entire macromolecule, moving. This happens in which of the following systems? Whether it happens in rubbers, or it happens in polymer melts, or it happens in glassy systems, or is it in crystalline systems or polymer solution? Where you could see the actual complete macromolecular motion.
Complete macromolecular movement is in happen in polymer solution only.
Only in
Molecular movement.
only in polymer solution.
Yes, polymer melt. If it is some bulky groups or side chains are there, it's very difficult.
Okay. 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 Any other answers?
No, there is crystalline is a very solid state. Glassy with a very means it's a amorphous stage. There is also mobility is restricted. Rubbers is in between the crosslink. There should be some movement. Nothing else.
Okay. Okay. You almost got it. Yes. So it's actually polymer melts and polymer solutions. Polymer melts also you find macromolecular motion, but there will be, as you said, depending on side groups and all, there will be some restrictions. There might be some difficulty, but still you can find some macromolecule, the entire macromolecule moving. And polymer solution, since it is again, you have a lot of solvents there, you can see the macromolecular motion. Okay, these are the two systems where you could see macromolecular, the whole molecule moving. And as you said, in rubbers, so in between the crosslinks. The segmental motion only happens. And glassy state, again your motion is frozen, and only you may have some side group motion and bond vibration. Okay, and crystalline states you will find only your bond vibration happening. Okay, not big of a motion you will find. Okay, hope you all got it. Understood? You all got it? I guess you all got it. Let's proceed. Orientation correlation is dash for small I and large dash for large I. So if the I, the number of the segments, or if it is smaller, then if it is close by, then you have a better orientation correlation. Or if it is at a at a at a you know you have a large I or number units, then you have a better orientation correlation. In which of these you have a better orientation correlation? Or whether you really have a orientation correlation in both?
I don't have any idea because I was absent during that time.
Okay. Okay, anyone else? Someone else wants to try? Or shall I proceed?
Proceed. That is better because I don't have any idea.
Okay, okay. It is actually strong when your, ith bond or link is close by. Okay, when the two close by bonds, you can have a better orientation correlation than, a large I. The first and some nth, which is a very large number. The correlation decays. It decays to zero as I increases, more and more. Okay, you can predict. Orientation correlation means you can predict how it might be orienting, right? Because of the bond restriction, the angular restrictions, and all those things. Okay, hope you all got it. Now let's go to the next question. The mean square end-to-end distance calculated from a freely rotating chain model of polyethylene is dash that of the one calculated from the ideal chain model. So you can calculate the mean square end-to-end distance for any polymer using these two models. Freely rotating chain model also you can calculate. You can calculate through ideal chain model, even extended chain model also you can calculate. So for polyethylene, you can find some correlation with the free. For everything you will have some correlation, some numerical correlation, but still here it is some direct number correlation. You can easily figure out from freely rotating chain model and the ideal chain model, mean square end-to-end distance that is calculated. What is it?
Is it a number we are talking about?
Yeah, yes, number. I think a lot of silence today. Let me proceed with the answer. It is actually twice. The one calculated from freely rotating chain model is twice that of the ideal chain model in case of polyethylene. Let's see how it is so. So ideal chain model, the mean square end-to-end distance is given by ns into a square. Okay, you all got it? Whereas in case of freely rotating chain model, you bring in the angle between the subsequent bond restrictions also. Here there is a bond restriction on, you cannot like have all angles for the CC bond. There are some particular angles only, so it is 109.5. so if you find the cos theta, here it is actually the relation is here is ns into a square into 1 minus cos theta by 1 plus cos theta. So cos theta, here theta is 109.5. So cos theta ends up in minus 1 by 3. If you incorporate by minus 1 by 3, you will end up in the mean square end to end distance to be 2 into ns into a square. Okay. So, and you end up with a twice the value. Do you know what is ns and a square? Ns and as here? Ns is the total number of bonds or links, and as is the length of each bond or link. Okay. So when you bring in the bond restriction, so in ideal chain it will be the end to end distance. So the chain will be much more coiled. You assuming it to be much more coiled, and it can take any conformation. Whereas here there is a restriction on the angle, so obviously it might be slightly extended compared to your ideal chain. So that is why you have the mean square end to end distance. You will end up with twice the value compared to that of the ideal chain. Okay. And then when you have steric hindrance, again that parameter adds on to the mean square end to end distance. And similarly, extended chain, again your excluded volume and all will come into the picture. Okay. You're all there?
Yeah, ma'am.
You got it?
Yeah, ma'am.
Shall I proceed with the next question?
Sure, ma'am.
Okay. Modulus of rubber dash with temperature. As the temperature increases, what happens to the modulus of rubber? This was given in a small box in your final lecture of the week. Not final lecture, the lecture 14. The size, shape, mobility and flexibility in that lecture. You can just say at least something, whether it increases with increase in temperature or decreases with increase in temperature. At least some guess you can make, right?
Decreases with increase in temperature.
Okay, why do you think so? Why do you think it decreases? Okay.
Wait. Because see, this modulus is stress by strain.
Yes. Yes.
So okay, force by area is constant. So stress is strain. Only strain factor is affecting. Temperature increases, strain increases. So that factor increases. So modulus is increasing. Okay. So temperature increases. The strain factor is increasing.
Okay.
So if strain factor is increasing, um, the strain value is increasing. So obviously it will decrease now, modulus.
So should we go ahead with the answer, the actual answer? It is actually modulus increases with increase in temperature. Okay. Why it is because, so now if you just consider the potential for a Gaussian spring, you will bring in this potential energy term. Okay, this potential energy, and then you can also just bring into the force in the spring, correct? So when you bring in, so energy by distance, so if you just take a derivative of the potential energy term by distance, you get the force, so you get into this kind of a system. So this force is equal to some kind of a factor with the multiplied by the material length factor, right? So this is something equivalent to F is equal to kx, so where x is the extension, F is this force, so k is nothing but your spring constant. So if k is spring constant, and the spring constant here, you will end up with 3RT by r square. Okay, here this r denotes the extension, and if you just bring it to the other side, you have 3RT into r divided by r square. So this becomes your spring constant term, correct? Hookean
Correct.
spring constant term. So if this is a spring constant, if you take it into the stress and strain, so your force by area gives your stress. Similarly,
Yeah.
this you can just get into the strain, right? The extension can be converted into strain, so that is nothing but, so the constant will be equivalent to your modulus, right? Where if you just replace force by stress and your extension by the strain, so the constant is nothing but your modulus. So if you just look into the modulus here, it is actually directly
Force by
proportional to
extension.
temperature, where T is temperature, right? So spring
Yeah.
constant is directly proportional to temperature, that is nothing but modulus is directly proportional to temperature. So that means the modulus increases with increase in temperature. So this is based on the Hookean concept,
Okay.
okay? For rubbers, as you said, for many other materials, it actually, the modulus actually decreases with increase in temperature.
Yes.
Okay, okay, I think that's it with the practice assignment questions. Hope you all got the last part of it, the Hookean spring concept and the potential. Hope you all got it. The potential energy of interaction, the psi c. So the psi c, so the energy, differentiating energy with respect to distance, you will get into force, right? Some basic mechanical concepts.
Uh,
Yeah, I'll look into.
Hello, madam.
Yes, yes, yes,
You just mentioned based on this Hawkins law. So,
yes.
can you explain with this phenomenon? Can you explain this phenomenon with some physical explanation why it's increasing? But normally, because we see that when the temperature increase like above Tg, the modulus of elasticity is decreases for all of the polymers.
Yes,
So, is there any assumption or why
see,
this things
again,
happen?
you're looking into the rubbery state only. Rubbery state, right? This is after TG, right?
Okay. So you mean these things after TG, after the glass transition temperature, these things happen?
It's not only about the glass transition. Maybe I'll just get back to you with the further, insights maybe in the next session. But here, theoretically, based on this Hookean spring model, it is directly proportional to the temperature. But as you said, in general, with temperature, that is where, the modulus decreases, and that steep decrease in modulus with temperature, where it starts decreasing steeply, you get the glass transition, as you said. That is what is the glass transition temperature. But this is for the rubbery state. Okay, more on rubbery state, but I'll get back to you on the much more insights on this maybe in the next class. Okay, I'll just note down. Okay, I'll just note down on this. Okay.
Okay, madam.
And you need some physical insights, right?
Yes, that will be help to remember the things actually.
Okay, okay. Let's just go back to the physical insights and then see it. Okay, so this ends the practice assignment questions. I just want to discuss a small question. This was posted in the forum in the previous year, July November 2022 of the same course. What was the question is that this was posted actually in the week 2 questions. Okay, the question was, at room temperature polyethylene polystyrene exist as plastics. Natural rubber, NBR, SBR exist as rubbers. But biopolymers such as proteins, polysaccharides, polynucleotides, how do they exist? This was a question posted by a student in last year, the same course. So, what do you think might be the possible answer? Any thoughts? Maybe I'll just show you the answer. See, one thing in the question itself, there is one small mistake. Polyethylene at room temperature is in rubbery state. Now, coming to the major question, how do the biopolymers such as proteins, polysaccharides, and polynucleotides exist? So it is actually a very complex, answer. So this biopolymers can exist in one of these following states. So one is it is dissolved in aqueous solution. So the molecules, macromolecules are solubilized in this case, implying very close interaction among solvent molecule and polymers. Okay, they can also exist as aqueous dispersion with a crystalline state, especially in case of proteins, or partially crystalline state, implying some portion of molecules are crystalline and some other are solubilized also. Or if you just take into the powder form, so these materials they are also freeze dried. So if you take it in powder form, that freeze dried form it may have a crystalline region as well as an amorphous form. Okay, and if it is going to exist in amorphous form, the dry biopolymers will be in obviously in glassy state. However, once you add water, they can plasticize the system. Okay, reducing the glass transition temperature. Okay, the plasticized biopolymers will be in rubbery state. So it's not a very straightforward answer, but it can be in one of these following states. Okay. Hope you all got some insights with this question and the corresponding answer. So, got it? Some new insights? I need some reply whether it was very useful or
No,
not.
the thing is that in biopolymers, the problem what I am thinking like that the biopolymers which reside inside a living cell is different than it is in the
Yes,
outside the cell.
yes,
That's
yes.
the thing.
That's perfectly true. Again, inside the cell, see, you have, it might be interacting with solvent like water in the body, right? So the state will be completely different from once you extract it and bring it. So after extracting and taking out itself, you depending on the application and depending on the work you do, it may exist in these forms. So inside the body again, it may again it will have some crystalline region, amorphous region, and it may be interacting this with the solvent in the body. So again, different kind of interaction and different form it will exist in. So it's not just a easy straightforward answer that it will remain in this phase and it will not remain in that phase. That is what the idea is about. Hope you are clear.
Yes, yes.
Okay, that's it with the session. So any other doubts, any specific doubts you have that you want to get clarified?
Ma'am, can you hear me?
Yes, yes,
Uh,
yes.
I have a doubt, but not related to this lecture.
Okay,
Okay, actually, this is time to register for exam, right?
okay.
Then, for how many exam can we write in one day?
I'm really really not sure. You may have to write to NPTEL actually on this.
Okay, then if
Okay,
we
actually
join for,
someone is answering. You can write two exams. I think Kirtivasan, he is answering that you can write two exams, morning and afternoon.
okay,
Okay, there
then
might, I mean, for the same course you're asking, I think there might be two sessions, I guess. I'm not sure really. Maybe you can just write to NPTEL or for the same course you're asking, is it?
yeah. No, no, no. If we join for more than two courses,
Okay,
then
okay.
for that all subjects we cannot write exam in the same day. That I am asking.
I'm really not sure. You just have to just check with the NPTEL. Okay, if it is online exam and if they permit, then you can easily take. If it is offline exam in particular centers and that center has that particular course exam being offered, then it is easy, right? Otherwise, you have to rush between centers. Just check with NPTEL team. I'm really not sure on this. Okay, I
Okay,
think
thank you.
Kirtivasan, he is answering that it is mentioned in the guidelines. So check in the
Yeah,
guidelines.
I go through that guidelines, but I could understand that it only two exam, but then why we are joining more than two courses, right? Like that.
Okay, okay, okay. But all the courses will not have exams on the same day, right? I don't know. I'm really not sure on that. Whether it is having exams on the same day or different days. You just have to check with the NPTEL team. They are, the
Okay,
right
ma'am. Okay, ma'am. It's
people
okay,
to
ma'am.
answer you
Okay,
precisely. Okay?
thank you, ma'am.
Yeah. So any other doubts? Any other doubts or anything else you want to be added to the session content? You want more numericals or you want some particular concepts which are to be brushed, any specific requirements, more numericals you want. Okay, probably we'll start doing that from the next session, because these two set of week 1 and week 2 lectures are all just giving basic idea into the course and just starting into the course. So maybe if week 3 content, it will have, I guess, on glass transition and all. I think you will have much more of you know uh, uh, where you can do a lot of numericals and all. So you might be having more numericals in the following session. I'll try to incorporate more numericals in the session. Any other specific requirements? If
Madam, can I ask one question
yes, yes, yes.
regarding the course content? Is there any course regarding the photopolymerization or photopolymer related any content will be updated in future? Do you,
On what?
on
Auto
the photopolymerization or the photopolymer
auto polymerization, you're saying?
photopolymerization?
Can you just type in, because your voice is not so clear? Can you just type
Hello.
in?
Yeah.
Can you just type in the chat box so that
Yes, please, madam. I just say the photopolymerization.
because on polymerization techniques and all, no, there is one more course. I think it was mentioned, photopolymerization. Okay, okay, okay. Photopolymerization or okay, is it related to photopolymerization? See, more on polymerization techniques. There is one more course that is offered. I think it is mentioned in the one of the lecture content, I guess, in I think in the lecture 9, where polymerization and depolymerization was discussed or something. Another course on polymerization techniques was mentioned, taken by some other professor. It is mentioned in the, if you just look into the lecture content, you will get to know what is that course. Maybe you can just go and check the course content of that particular course.
Okay, okay, ma'am.
Okay, maybe that might help you. Yeah,
Yeah,
or
okay, ma'am.
yeah, you can just check that probably. Because it is mentioned on polymerization techniques. there is a separate course, and maybe that course you can just go through the course content of that particular course, so that you can just check if it is if there are contents on photopolymerization. Okay.
Okay, madam.
Yeah. Yes. Is there any other questions? If there are no further questions, then we can officially end the session.
Ma'am, about monodisperse polymer, we have been we should be achieving polydispersity rate, ma'am. Like anionic, any other polymerization techniques for achieving monodispersity?
No, see, anionic polymerization is what that gives very, um low dispersity, you know, closer to monodispersity you get. Uh, there is, I think step polymerization, it again depends on the extent, and you may get around something closer to 2. That is also, I think, given in the lecture content, I guess. Yes. It
Yeah,
depends
ma'am.
on the conversion actually. I think it is 1 by 1 minus p or something. If I'm right. Yeah, it gives something closer to 2 step polymerization. Uh, yes.
Like special polymerization techniques like raft and ATRP, will it give monodisperse index?
I'm really not sure. Really not sure on that.
Okay, ma'am.
Uh,
Sure.
yeah, you maybe I can just note down the question, and then maybe if I'm able to find an answer, I can just answer for that. Well, what are the techniques you said?
Raft, ma'am. RAFT.
Ra.
Radical additional fragmentation technique.
Okay, and
RAFT and the ATRP.
okay, ATRP. Does it give monodisperse, right?
And group transfer chain reaction, chain polymerization, GTC. Will it be able to give monodisperse?
Polymerization. So does it give monodisperse? So polymers. I'll just check and maybe let you know in the future lecture.
Sure, ma'am.
Yeah, and I request you all to post it in the forum also, so that uh, that will also get recorded, so that
Okay, sure, ma'am.
anybody else uh, who sees that question, they'll also have some thought about it, and uh, they can you know they also get some insights. Okay.
Okay, ma'am. Thank you, ma'am.
Okay. Okay, anything else? If not, no other questions, then we can close the session. Thank you all.
Okay, ma'am.
Thank you
Thank you,
all.
ma'am.
Let's meet on Saturday then, 4 to 6.